Welcome to the Astronomers for Planet Earth webinar series, hosted by Dr. Travis Rector, Professor of Astrophysics at University of Alaska, Anchorage. Today's guest is Dr. Oliver Elbert. Dr. Elbert received a BS in Astrophysics from Haverford College and a PhD in Physics from the University of California Irvine, using cosmological simulation to study galaxy evolution and dark matter. After receiving his PhD, he left the field and is now working on climate models at Vulcan, Inc. and NOAA's Geophysical Fluid Dynamics Laboratory. He is part of a team that's developing a domain-specific programming language to run weather and climate simulations on the next generation of supercomputers, as well as implementing NOAA's finite-volume-cubed model in their DSL.
Hi, everyone. My name is Travis Rector, and I'm a professor of physics and astronomy at the University of Alaska, Anchorage. And I'm also one of the organizers for a group called Astronomers for Planet Earth, which is working to help astronomers better understand the causes and consequences of climate change, as well as solutions. And for our webinar today, we are delighted to have with us Dr. Oliver Elbert, who is a researcher working on the modeling of climate. And he has a fascinating backstory. He started in the computer modeling of cosmology and then has moved to a significantly smaller scale. Oliver, welcome and thank you for joining us today.
Well, thank you for that introduction, Travis. I'm really excited by the opportunity to talk to you all, as well as to discuss climate modeling, a bit of my work with climate models, as well as my transition from astronomy to climate work. So I guess to begin with, I got my PhD from the University of California in Irvine, where I was running numerical simulations of galaxy formation and evolution on big supercomputers like NASA's Pleiades. It's actually a picture of me in front of the building where they keep Pleiades when I was in town one day. And even though I brought a tray of brownies, they refused to let me in the building. So I defended in 2017. I was on the job market in 2016. And actually, I really liked the slide Rachel Mason showed in her talk with the sort of scariness spectrum. And as things get more serious, you start feeling like you have to get more involved, maybe first extracurricularly, and then eventually as your sort of full-time day job. And in the wake of 2016, that was on my mind, and combined with some personal reasons, I decided to leave academia and try to get more involved solving problems like climate change. And this was actually difficult for me at first. I wasn't sure where to look or how to go about it, because I'd been planning to stay in academia for all of my career up to that point. And eventually I first had a job that was very cool, working on satellite tracking and space traffic management. But then in the fall of 2019, Vulcan, Inc., which is Paul Allen's holding company, was looking to start a climate modeling team. And they specifically needed someone with experience running numerical simulations on supercomputers as a domain scientist in order to embed with their partners at NOAA. And this was a great fit for me. It really scratched that itch of wanting to work on problems like climate change. And so now I'm embedded at NOAA's Geophysical Fluid Dynamics Laboratory, where I'm helping to develop a domain-specific programming language for weather and climate modeling. And I think the transition for me to climate modeling was in a lot of ways very similar to the transition to working on data science and software engineering in my previous job. I think one big thing is your network. I heard about the Vulcan job through actually a friend from grad school who's also on Vulcan's climate modeling team. And then the other part of it is understanding what you are good at, what the skills are that you've developed in your career so far as an astronomer, and how that overlaps with the needs and the work for the people or the project that you want to contribute to. So as a simulator, for me, that was a lot of computer programming and running numerical models on supercomputers. So that transitioned very nicely to climate modeling. For an observer, though, I mean, we have a wealth of observational data from satellites, from oceanographic surveys. And if you have experience, dealing with raw instrument data, I think that could also be a really great way to contribute, whether, again, if you want to have this be something you do in your spare time or start maybe an interdisciplinary project, or, like me, just want to devote yourself to it. So as I said, I was a simulator before, and I'm kind of a simulator again now. And the overlap between large cosmological simulations and climate models is actually non-zero. There's a lot of similarity. You have a chaotic system that you're using computational fluid dynamics to solve, like a finite volume method. And these are run on large supercomputers. So MPI and OpenMP parallelization is everywhere. But there are naturally a lot of differences. I think the biggest one actually is just the fact that when you're running a weather or climate model, you know what the problem geometry is, right? You have a sphere that has a set angular momentum, whereas if you're running a Milky Way analog simulation like Latte at the top here, when you're first starting the simulation, you don't know what the orientation of that galaxy will be. You don't even necessarily know where in the cosmological volume it will be until you finish your unigrid initial run. And so that opens up a lot of room for aggressive optimization and sort of changing the numerical scheme for weather and climate models compared to a cosmological simulation. Another big difference, is just the sorts of things that you have to model and handle. So for example, for a cosmological simulation, you have your hydrogen, your helium, your metals, and those don't really change into each other unless they go into a star and then come out sometime later in a supernova. Whereas for a climate model, in the atmosphere, you're tracking rain, water vapor, snow, and these tracers can, phase change into each other, from time step to time step. And so you have to, the processes that you're modeling are very different. Another big difference is that the data that you use to initialize your model can be very high resolution. There's some atmospheric models being run now with data that's sampled on a kilometer scale. And at the same time, that also means that the demands that are made of the model can be very specific, which is not to say that, astronomers are lax in our accuracy, but I think if the weather forecast had the same, level of accuracy as, say, the stellar mass-halo mass relation, you might not trust the tail end of your 10-day local forecast. Also, one thing that I should say is that I've been talking about weather and climate modeling and sort of using those weather models and climate models interchangeably, and I'm going to continue to do so throughout this talk. And the reason for that is that the underlying code that runs these models is very similar between, it's really, for the most part, the same between a weather forecast simulation and a climate model run. And so to go into a little bit more detail with that, the basics are fairly similar. As I said, you have, you're simulating the Earth, so you discretize it into grid cells. So here on the upper right is a mnemonic cubed sphere, like what many NOAA models use. And so for a weather forecast simulation, these grid cells will be maybe a few kilometers to 10-ish kilometers on a side. So you have 10 to 50-ish million of these cells covering the Earth horizontally, and then around 100 or so vertical levels to model the atmosphere, for example. Whereas for a climate simulation, you have many orders of magnitude fewer grid cells generally, and also about a third as many vertical levels. So you really are simulating at much coarser resolution, which is necessary because, instead of simulating for 10 days or so, you're now simulating the Earth for a decade, a century, some extended period. But the inner mechanics of these models are, fairly standard. You have some flow that carries mass from one cell to another. So in that atmosphere, this is wind moving across the Earth's surface or in the upper atmosphere. in the ocean. This will be current flowing and carrying water. And then these flows also carry some tracer species like the rain, water vapor, and such that I mentioned earlier. One thing, as I said, because we know the problem geometry, we can make some use of some aggressive optimizations and some approximations that you can't in a cosmological simulation. So you can do things like have your grid be deformable in the vertical dimension, or you can use a hydrostatic approximation and ignore vertical wind motion entirely. Although that, again, is usually only in place for very coarse simulations. And then all of these models have things that they don't directly resolve, and so they have to apply these subgrid parameterizations. So for example, cumulus cloud on the bottom here is, there's a lot that happens in a cumulus cloud. There's a lot of structure you can see. There's a lot of dynamics inside the cloud. But in a climate simulation, this may only take 3 grid cells. And so you can't actually directly resolve any of that structure or any of the physics that's happening internal to the cloud. And so you need some algorithm to apply in order to correctly account for that in your climate model. The other thing about climate models is that there are actually many models. So this is kind of a schematic cartoon of that, where you have the amount of time dedicated to each sort of constituent model on the y-axis, and then the x-axis shows the number of processors dedicated to it. So the area of each box indicates the computational intensity of each submodel. And these, handle modeling the ocean, the atmosphere, as well as the land and and sea ice on the surface of the ocean. But like I said, the basics are fairly straightforward. Again, you have your result for each of these models. You have a resolved portion, which is in the atmosphere is the wind dynamics, and then that wind carrying tracers around on the Earth. For the ocean, that would be the current dynamics carrying tracers. And then you also have your subgrid schemes. So in the atmosphere, you have to deal with radiation, turbulence inside of each grid cell, convection in the lower atmosphere, the cloud structure, which I showed on the previous slide. For the ocean, again, you need to handle turbulence, convection. There are multiple boundary layers that you also have to treat specially. And then the land surface is responsible for things like land use, hydrology, ecology, and sea ice handles the growing and shrinking of the ice in the Arctic and Antarctic as seasons change, and also as the Earth warms, as well as the motion of icebergs and the sort of energetics associated with that. So that's all sort of what a climate model is roughly. The next question is, that's all well and good. How do we know that we can trust what they say? So one thing that climate modelers do to validate their models is what's called hindcasting, where they'll initialize a simulation with some previous state of the Earth's climate and simulate forward in time. And then as the model progresses, they can compare model predictions with what actually happened in the Earth's history. So this is a plot of the global mean temperature for simulations that were run around the year 2000, but initialized in 1970. And you can see that in those 3 decades from 1970 to 2000, these models do a very good job of reproducing the evolution of the Earth's temperature over that period. And then since these were run in 2000, we can also take the predictions that they made for the subsequent 20 years and compare them to what actually happened. And we see that the projections of these models also do a good job matching the observed changes in the Earth's temperature from 2000 up to now. Another method that's used to make sure that climate models are accurate in their predictions is the use of ensemble simulation. So the blue band here actually shows the 95% range for a large number of models that were actually run in order to make these predictions. And you can perturb each of these models by the uncertainty in the initial conditions, in your observational data, as well as the uncertainty in your numerical approximations. And so by running a large number of models, you can have a good idea not only of what the expected behavior is, but also how certain you are based on your understanding of the physics and how well you're representing the physics, as well as your knowledge of the Earth's climate itself. One other thing that I think really also gives a lot of confidence in climate modeling generally is the large differences between a lot of these climate models. I made a point earlier that generally things are fairly straightforward. You have your dynamics capturing the motion of things around the Earth, and then subgrid approximations to handle things you can't directly resolve. But each different climate modeling team has their own climate model, like the differences between gadget and say gasoline, for example, or art or Ramses. And so these things, these different models can have different grid discretizations. So there was the mnemonic cube sphere I showed earlier, but also some groups use a latitude-longitude grid. Some groups use an unstructured mesh to discretize the Earth. Different numerical schemes are used. So some groups will use a semi-Lagrangian scheme. Some will use spectral methods. Also, each physical or subgrid approximation, will differ from climate model to climate model. And so the fact that, even with all of these differences in the numerical approach, all of these climate models consistently tell the same story and give us the same predictions for, the Earth's temperature increasing and increasing as carbon dioxide continues to flow into the atmosphere, that really is, we can really be confident in those predictions. So I'd also like to take a little bit of time actually to talk about some of what I'm doing with domain-specific languages. So like I said, we're building a DSL for weather and climate modeling. And a domain-specific language is just a programming language that's been specialized for one purpose or for one domain of computation. So TensorFlow is a DSL for neural networks. LaTeX is a DSL for typesetting. And to give some background in this, supercomputers are moving to GPU programming. This is on the left, a plot of the top 10 fastest supercomputers in the world as of November of last year. And 7 of these use GPUs in order to accelerate their programming speeds. And so being able to run on GPUs is really necessary in order to fully harness the power of these machines and to run efficiently on them. And this also is an opportunity, right? The GPU is there to increase the programming capacity. So being able to run on a GPU means that you can run your current models much faster. And so in the same amount of compute time, you can have a larger ensemble for your ensemble prediction and gain much more statistical power in your model. Or you can also sort of go through an orthogonal approach and directly increase the resolution of the model, which lets you bring more processes from the subgrid scale into the directly resolved regime. And this also will help increase the predictive accuracy of these climate models. And there are a few ways that you can go about porting to GPUs. You can rewrite your code in CUDA or something similar, but then, well, one, you have to write CUDA code, which is pretty low level and can be a bit of a change from some of the Fortran models that are currently popular throughout the climate modeling community. And then you also have multiple code bases that you have to maintain, right? One, a Fortran model to run on CPUs and a CUDA model to run on GPUs. You can also make use of compiler directives like OpenACC, but this complicates the code a lot and can also require some pretty extensive duplication of different parts of the code in order to really fully achieve the performance you want to get out of a machine like this. And really with either of these approaches, you would have to do the same thing again if in 10 years, instead of GPUs now, maybe tensor processing units or FPGAs are becoming dominant in supercomputing. And so the approach that we've taken and that we are working on and advocating is to use a domain-specific language where you write your model actually in Python, and we have a compiler that then takes that Python code and turns it into heavily optimized C++ or CUDA code based on a keyword that you set to determine what backend you're running on. And there's an example of this on the right here, and our code is also open and available on GitHub. So you can sort of check it out, see what it looks like, see what how a climate model works if you like. And by doing this, it means that your code can be fairly simple. You only have one code base you need to maintain. Actually, this code is pretty clean, right? Especially in comparison to some very heavily optimized, C or Fortran codes. We have the use of functions. We have names that are more than 6 characters long. And this actually is kind of another big benefit of the DSL approach, where traditionally a modeler is responsible for everything from the PDEs that describe the system they want to solve and the physics that they want to model, all the way down to the nitty-gritty of the optimization of the code on the supercomputer. And because the DSL handles the optimization and even guides a lot of the numerical implementation, that frees up the domain scientists to focus more on their science, whether that's running more and spending more time analyzing their models, all of these kinds of things. And the other thing is that having this nicer code means that it's a lot easier for new scientists and graduate students to pick up what's happening, how these algorithms are working. And that's part of why we chose Python as our front end, is for that increased readability and adoptability. I mean, I know when I was in graduate school, if there had been a version of Gadget that was written in Python that I could run on Pleiades, I would have jumped at that. And so, we really think the DSL approach combines really the best of both worlds, where you can have the readability and usability of a high-level language like Python, as well as the actual raw performance of something like Fortran or like C. And the reason that I bring this up is because I think that this has applications beyond just climate science. I think this could be really useful potentially for astronomers as well. Maybe it's not quite a fair comparison because we have a team of software engineers and computer scientists who are developing this DSL, but there's been a lot of talk in the astronomy community about reducing carbon footprints, and part of that is from reducing the carbon footprint of these large numerical simulations that get run. That was something that I had a lot of conversations about when I was in grad school. And I think that having some kind of DSL that you can use for a cosmological simulation, or maybe simulations of supernovae, could be really useful, again, for both increasing the performance of these models, as well as for making the lives of grad students and younger scientists easier. And that, I think, is potentially an interesting thing to think about in terms of interdisciplinary work, maybe with somebody in a computer science department. And I don't actually really have a conclusion for this section of the talk. It really intended it more as a jumping off point and a way to spark discussion, which I'm very happy to have. And so with that, I'd like to thank you very much for your time and your attention. And again, thank you, Travis, for the opportunity to talk about this today.
Oh, well, thank you, Oliver. That was really interesting. And I have a lot of questions for you, and I know our audience will as well. So I look very much forward to the Q&A session. So thank you again for your time today.
Thank you very much. I really, really appreciate it.
We hope you've enjoyed today's talk. Each of our talks is followed with a Q&A session that you can learn more about in the video description. If you're interested in Astronomers for Planet Earth, you can learn more at our website, astronomersforplanet.earth, and on social media as well. If you would like to be notified about future talks and events, please follow and join us.